Okay, so on this set of slides, instead of having some code that we're going to step through and coming up with total running time, you can basically say that I've given you total running time here, and I've given you the big O upper bound on the total running time, and we just want to prove that that claim is correct. So we're not going to worry about working through code here. This is going to be a little more abstract. So what does this mean? 2 to the n plus 10 power is big O of 2 to the n. That's like saying 2 to the n plus 10 is less than or equal to some constant times 2 to the n for all values of n greater than or equal to n naught, looking for values of n naught in C. Okay, well, this is kind of, do you remember your algebra a little bit? There's nothing tricky about this unless you forgot this simple thought, which is that 2 to the n plus 10 is the same thing as 2 to the n times 2 to the 10th. And I will admit that doesn't readily come to my mind exactly when I see this, so this is simple, but only if you happen to have remembered that. Is less than or equal to some constant times 2 to the n for all values of n greater than or equal to n naught. We can just divide both sides, a 2 to the n out of both sides, so a good value for C here is 2 to the 10, and a good value for n naught. Nothing dropped out sort of from our analysis here, so that all the n's canceled out. We didn't have to do anything, so just, you know, as computer scientists, a good value for n naught is going to be 1. We're never going to run an algorithm on no input usually, so that's one way to think about it. So C is equal to 2 to the 10th, n naught is equal to 1. Alright, next one here. Slightly different. We had 2 to the n plus 10 on this one, now we have 2 to the 10n on this one. So the claim here is that we need to be able to find values for C and n naught that make this inequality hold. Well, now we don't have to separate anything out. We can just, you know, directly divide both sides by 2 to the n. And if you remember what this does, it's like putting up here a 2 to the negative n, which means we're going to have 2 to the 10n minus n is less than or equal to C, which is like saying 2 to the 9n is less than or equal to C for all values of n greater than or equal to n naught. Well, our claim was that 2 to the 10n is big O of 2 to the n, and it's not, because we cannot find a value for C that makes this inequality hold. Because no matter what you pick for C, if you increase n, C now no longer is greater than the left-hand side. So this claim is not true. So we would say 2 to the 10n is not big O of 2 to the n. Alright, so this one's fairly similar. And what our claim here is that for every value of k greater than or equal to 1, n to the k is not big O of n to the k minus 1. So that'd be like the not equal that we had on the previous. Easiest way to do this is by proof by contradiction. So we'll just invert the claim, and we'll say that the claim says that for all values of k greater than or equal to 1, that n to the k is big O of n to the k minus 1. We're just inverting the claim. So instead of saying it's not equal, we'll say it is equal. So meaning that n to the k is big O of n to the k minus 1. Which means that n to the k is less than or equal to some constant times n to the k minus 1 for all values of n greater than or equal to n naught. Alright, well, we'll just do the same thing we did on this example, but instead of splitting up 2 to the n so we'll split up 2 to the n into 2 to the n and 2 to the 10th. What I mean by that is we'll split this here into n to the k and n to the minus 1. So n to the k is less than or equal to C times n to the k and n to the minus 1 for all values of n greater than or equal to n naught. Divide n to the k on both sides, and divide both sides by n to the minus 1 is like saying we'll have n over here and C over here for all values of n greater than n naught. Well, we cannot find a value of C that satisfies this inequality. There's no constant that's greater than an arbitrarily large value of n. So this is not true, which means the original claim So the original claim is true. Since our proof by contradiction, so since we inverted the proof, our original proof is true since we cannot satisfy the inverted proof. Alright, so here's our first non-big O example. So previously we've been talking about basically this. T of n is less than or equal to some constant times f of n. That gives you an upper bound. What do I mean by upper bound? Well, let's say that we have some function. It has some constant amount of work at the beginning, so it's never going to cost 0. But as n increases, maybe it increases like that. What we've been looking at essentially is an upper bound. We've been trying to find a function on this blue line that is always greater than the green line after you get to some value of n naught. So the blue line is always bigger than the green line after some initial startup costs that's usually associated with n naught. So for all values of n greater than or equal to n naught. Well, what we're doing now is we're saying not only do we have an upper bound, but we have a lower bound. So the green line is always greater than this blue line. Did I just say blue? This green line is always greater than this red line, the red line that I just added. And I'll dash it, just in case the red's not coming through for anybody. So this is called a tighter bound. We have an upper bound that's asymptotically the same as the lower bound. Because if you look here, we've got f of n on the upper bound side and f of n on the lower bound side. So that's different than saying like a function is lower bounded by, like saying a function's lower bounded by n and upper bounded by n squared. We're saying that it's lower bounded by n squared and upper bounded by n squared. So it's definitely always going to run sort of in that range. Alright, so the easiest way to do these proofs, well actually before we go through the proof, I just threw theta notation at you, but let me show you some of the other types of notation and how they correspond to one another. So what we've been doing is big O notation, which says that T of n is less than some constant times f of n. There's a corresponding lower bound, so this is your upper bound, this is your lower. So there's a big omega that says T of n is equal to big omega if T of n is greater than, always greater than or equal to some constant times f of n. So that's saying that the best case running time, or our algorithm will never run faster than, it's always going to be lower bounded by this function f of n. Well, theta notation is when you do a big O proof and a big omega proof, essentially. So we're saying that our running time is lower bounded and upper bounded by the same f of n. Clearly we'll end up with different constants here for C1 and C2. We will end up with just a single value for n naught though. And just for completeness sake, there's also a little o and a little omega, which gets rid of the equality part here. So instead of greater than or equal to, it's just greater than, or sorry, less than or equal to, it's just less than. But let's work through our theta proof here. So for theta proof, I usually start by doing the upper bound first, just because that's what we mostly do in classes as an upper bound. So here is, this should look somewhat familiar. This is our merge sort routine. So we kind of did this when we were looking at sorting and looking for duplicate numbers. So this would look pretty familiar, but we'll actually use an intermediate term this time. So we've got 21 n log n. Let me try to stick to my consistent notation here. N log n. This is 21 and not like 20, or not like 2 natural log. My handwriting can betray me sometimes. Plus 21n is less than or equal to some constant times n log n for all values of n greater than or equal to n naught. I'm going to use an intermediate term, and we'll say that 21 n log n plus 21n is less than or equal to 21 n log n, because 21 n log n is less than or equal to 21 n log n, plus 21, and I want to basically raise this thing to have the same highest order as this other term, so n log n. So to do that, I just have to multiply it by log n, and that's going to be less than n log n for all values of n greater than or equal to n naught. So the first thing I need to do is prove that this part is correct. And to do that, we could say 21 in log n is less than or equal to 21 in log n. So that's the first term. And that one's pretty trivially true, right? They're equal to. So of course it's less than or equal to. We also need to show that 21n is less than or equal to 21 in log n. So we'll divide a 21n out of both sides, which means we need to show that 1 is less than or equal to log n. Well, that's only true for values of n greater than or equal to 2. Log of 1 is 0, log of 1.5 is somewhere between 0 and 1, log of 2, log base 2 of 2 is 1. So we need our value of n to be greater than or equal to 2. Alright, so that part's done. We've got a value that we think we can use for n naught. And what we have here is 21 in log n plus 21 in log n, which is 42 in log n, is less than or equal to n. Oh, I dropped my c, didn't I? So there should have been a c right there. C in log n. So divide n log n's out, and we're going to have c is equal to 42, and n naught is going to be 2. Okay, we could do the same process, so I'll just note on this slide. Sometimes I'll do a big O proof here again using, instead of an intermediate step, dividing through by n log n. And what you'd find out here is that you'd end up with a c is equal to 22 and an n naught. There are different values you could get, but when I usually do this, an n naught is equal to 2 to the 21st power. What I encourage you to do is go through that on your own and see if you can figure out how I came up with these values, and if you can't, stop by my office hours, ask during the mentor sessions, ask me in class next time, and I can step through and help you out anywhere that you're having issues. Alright, but so we've done this part. That part's done. We had a value for n naught of 2 and a value for c2 of 42, I believe. 42. Alright, so now we need to do the lower bound part. So this is going to be our mega proof part. So to say that what we're going to do is we're going to say that some constant, and I'll use C1 here. I should have been using C2 on this slide, C2, and then C2 on this slide, and I just dropped it everywhere through, so this should be C2 everywhere. C2. C2 is going to be our coefficient term for the upper bound. So we'll have C1 on the lower bound. C1 times n log n is less than or equal to 21 in log n plus 21n for all values of n greater than or equal to n naught. And if we end up with an n naught greater than 2, we'll use that one. If we end up with an n naught less than 1, or sorry, less than 2, then we'll just stick with our original 2 that we had from the big O proof, the upper bound proof. So here, it turns out that using an intermediate step makes this sort of dead simple. So if we have C1 in log n, we're going to have an intermediate term just like we've had before. And on the upper bound, we'll have 21 in log n plus 21n. So I'm just grabbing our terms. What makes sense to put here in the middle that's definitely less than this, but definitely greater than or equal to this? Well, we know that n is going to be a positive number, which means that this thing is some positive value. So if I just remove that term, I can end up with something that's less than it. So we'll just put 21 in log n here. And this assumes that n is greater than or equal to 1. Well, we already had that n had to be greater than or equal to 2 anyway, so that's pretty easily satisfied. So 21 in log n is less than this. So now we can say that C1 in log n is less than or equal to 21 in log n. We can divide the in log n's, and we can say C1 is equal to 21. We had C2 was 42, and we have n naught is equal to 2 from our big O proof, because if n is greater than or equal to 2, it's certainly greater than or equal to 1. Alright, so let's just kind of summarize what we've been doing here. When you do a theta proof, what you're really looking for is that line that's going to upper bound. Use a highlighting color. You're looking for that line that's going to upper bound your running time function. So this is your total work function that we've spent a lot of time trying to figure out. And we just want to say our running time is upper bounded. A lot of times you also want to say that it's lower bounded by the same function. That gives you a little more confidence in what the average running time is going to be. If sometimes it runs in constant time versus not constant time, that kind of thing. So to do this, to say you have a tight bound, to say you have a theta proof, so to say that your function is theta of some function, you do a big O proof, so you say t of n is less than or equal to some constant times f1. You do an omega proof, and those two things combined together give you give you the theta proof. And where does your value for n naught come from? Well, typically your total running time will have some weird characteristic where it has some non-zero startup cost of constant work that you do even if you don't have any elements. So just like analyzing the input or something like that. Which means that your upper bound is not always greater than that. It's only greater after some point here and not. Alright, so let me just give you an example here. You should pause the slide here and tell me sort of, just by looking at what we have over here, what is f of n? What would be good values for c and n naught? Alright, well, hopefully you've had a chance to pause it. Well, f of n, so in case it wasn't obvious, which I would say it's probably not obvious, our upper bound thing here is going to be the blue line. That's going to be our upper bound. And usually our upper bound is some constant times f of n, which means that f of n is going to be our n squared from here. Well, what's a reasonable value for c? C is kind of just given to you there. It's 2.5 from here. And how about n naught? Well, for n naught, I think a value of, I don't know, 5 or 6 makes sense. I don't know if 5 is quite big enough, so let's just say 6. And where does that come from? It comes from where the blue line crosses over the orange line and is always, from then on, strictly greater than. And that's because we've gotten rid of sort of this pesky constant term here, because our f of n is never going to have a constant term. We don't need that. Alright, so again, let me just summarize why this is important. Let's say we have two computers. We have computer A, and that's going to be some sort of supercomputer running at 10,000 million instructions per second. So 10,000 million instructions per second. Let's say it's running a pretty efficient version of insertion sort, so 2n squared. You're only doing 2 operations in your loop. We ended up with, what was it, 21? No, what was it? I don't remember what we had for insertion sort running time, but it was certainly bigger coefficient out in front of n squared than 2. And let's say we have computer B, which is your calculator, 10 million instructions per second. So not a very strong computer there. And let's say it's running merge sort. How long does it take to sort 10 million numbers? Well, the supercomputer is going to take 5 hours, and the calculator, the low-end device, is going to take 20 minutes. What if you're doing 100 million numbers? Supercomputer takes 23 days. Merge sort on the calculator takes 4 hours. That does assume that all the data fits on the calculator. 100 million numbers is pretty reasonable to fit on a calculator, though, I think. So this is why we care about big O asymptotic complexity, because you might get confused here and say, well, the 50 is bigger than the 2, but really what this side is big O of n squared. What this side is big O of n log n. N log n is a faster algorithm than an n squared algorithm. All the constants and leading coefficients and lower order terms don't matter. We want to use merge sort. Alright, so what are we doing here? We're simplifying the comparison. Can we remove leading order coefficients? So leading coefficients would be like the 21 n log n plus 21, and the leading coefficient would be this thing. the lower order terms would be removing the terms that aren't at the highest order of n. Because both of those things are very insignificant compared to the growth of the function. What's the growth of the function? Let me use a third color. The growth of the function is just the highest order of n. So basically those other things get factored into that constant c when you do the proof.